Good afternoon. So is the hello? So the slide is visible.
Yes, sir.
Okay. So we were discussing about SVM and what we basically have discussed in the last class, that we are trying to find out a linear discriminant function, or for technically it is decision boundary. This is a linear decision boundary, so that we can efficiently distinguish between different classes, the data points in different classes. Mainly we have discussed about the binary class. Now, what we have seen, that in spite of getting a single line, we can have a kind of uh, the fat margin classifier, that we can say fat in that sense. There is some width of this decision boundary. At the width, you are getting the more thus robust the decision boundary. So here we formulate this particular problem in a bit different way, so that we can have a mathematical formulation of such this particular problem. Okay, so here you can see that there is a two class problem. So there is, you can see that, let's see, there is a two class, binary class problem. There's two classes, C1 let and C2. So that you can think, and your decision boundary is denoted by some arbitrary function, that is gx, that is theta is w transpose. W transpose x plus, let's say b0, or let's say b. Okay. So this is your, basically this is wx, this is the decision boundary. Now we can say if this gx is equal to this, then this particular thing, it is basically useful in a two-dimensional case. Okay, kind of two-dimensional case. So it can be in a multi-dimensional case, it can be. So then what is this w, this particular w is basically, what is this w? This w is the orientation of hyperplane in, let's say this is two-dimensional place, but in case it is three-dimensional place. space. So it is a, it may be, if this is a d-dimensional space, then it is a, the actual, then the data points is d plus 1 dimension. So that is okay. That's not a big issue. And what is B? B is basically a bias term that give the position of the object. So now you can see very easily that what is the idea is basically this. If it is this is, then it is y is equal to mx plus c, but c is equal to 0. And if it is giving same thing, if it is going to in this way, so this term is b. So it is mx is equal to plus b. So this is equal to y is equal to. So this is y is equal to mx and this y is equal to mx plus b. So that is the thing. Okay, so this is the idea. Now, the question is that if idea is that if g of x1 is basically the point if greater than 0. So what does this mean? That means wx1 plus b greater than 0. If it is, then we can say x belongs to, x1 belongs to this point. So this is, since it is a positive, so this belongs to positive plus. And if this is if, this is if, and if this wx1 plus b less than 0, then it is basically, you can say there is a wt. So okay, so is less than 0, then this xi is belongs to negative plus. Fine. So that is the idea. Fine. And definitely, if for some xi, if wtx plus b for, or better to say wtx xj say is equal to 0, then xj is on decision boundary. So इसका ऊपर है, there's some point on that line. So this is the way we classify the data. Okay. Now the question is that this is the basic understanding. But in a supervised classifier, this is what we said. Now the thing is that in a supervised setting, if you say in supervised setting, what do you mean by training of this classifier? How you know? So that idea is that this wf of x wb. So what we have to giving the examples, giving the training examples, or training, better to say training samples, we have to find this w and b. That means the training. So w and b means what? WB means what? That what is that will going to fix this line. Okay, this line is basically parameters with W and B. Okay, so and that means these data points, but there is a lot of way to do that. We can get a different values of W and B, and if we get a W and B in this way, or W and B different in a multiple number of ways. So any of these would be fine. Please mute you. Please mute your microphones. Now the question is that which of these is the best? That these are the infinite number of, say, or a very large number of decision boundary. They try to find which decision boundary is the best. Now I formulate the problem of support vector machine in this way. Okay, so that is the question. Now see, now let this is the thing, and the idea is that you choose a decision boundary, something like that. Okay. Now let there is a point here. Now this is positive, this is negative. Okay. Now since it is here, left hand side of this decision boundary, this point is basically is a positive plus. Okay. So but the now this is misclassified kind of thing. Because this may be very close to these points. Now we can get this. This is much, this particular thing, this decision boundary is, you can say, more well separate the data points. And how it will going to separate data points? You can see that this there is a define a margin of a linear classifier as the width that the boundary could be increased by the before hitting a data point. So we can put, you can say that we can lay the margin around this decision boundary. And this is called what we have discussed, the high margin classifier. High margin, if you increase this margin, the robustness increased, the classifier will be more robust. That is the simple idea. Okay, so that is the idea, that can we find this higher margin classifier. In that way we define this particular. So that particular thing we decided earlier in this way. Okay, so there is some point. There is some point. Let's say here. This is, and what we can do, we can this a kind of a, okay, so this is the basically the margin, and just excuse my drawing. This is the straight lines. Okay, so this is the width. So this is the width of the decision boundary. Okay, and this we have discussed in this way, that what we have discussed from a logistic regression viewpoint, and we have shown that how actually this classifier will going to give you how the loss function of this logistic regression have changed to get this. Okay, so that is the same thing. Okay, what I'm trying to say, this is there is no difference. Now you can see that this fat margin classifier, that is how we can get this. Also we have discussed, we said that there is some sort of samples, data samples, that data samples are going to help to find this. So you can say from a very intuitive point of view that the data sample which are very close to the decision boundary, that will give, that will drive to find this decision boundary. Here also you can have decision boundary. Okay. So that data samples, we'll see that this kind of data sample that we find is a more important. Simplest this. So this maximum margin, so this data sample is called support vector. We'll come into that. And this maximum margin linear classifier is the linear classifier with the maximum margin. Okay. And this is simplest kind of SVM called LSVM. So, okay. So now the question is that these data samples are going to find this point are called support vectors. Are those data points that margin pushes up against. So these data points are going to help you to find out this. So what is actual our goal here? We have to find the maximum margin. How to get this margin? How to make this margin maximum? Okay. So you can say, so the basic proposition of this particular problem, maximizing the margin is good according to the, so PAC will come later. It's called probably approximately correct. That is actually that when we go to the kind of more theoretical aspects of machine learning, we'll know what is the PAC theory. But it is a kind of a theory based on this. It has been defined. Implies that only support vectors are important. Other training example is not that much important. Empirically, it works very well in that, to find out this. Okay. So one thing that is important, that support vectors are important in case of find this maximum margin, not other. So it don't confuse it to other things. Okay. So this is the total very geometrical way or in the visualization of the problem. So this is the basic idea. Now we will try to find out that some mathematical formulation of this linear support vector machine. Okay. So basically what we're trying to find out, we're trying to what is our goal? Just a second. What is our goal? So that goal is the maximize the margin. So this margin we have to maximize. Okay. So now you can say x I, that is that xi means just a vector, is, let's say, positive class or belongs to that means class C1. Okay. So if it is so, that we can get this value, that W transpose xi plus b is greater than equal to 0. So that is basically our intention, because xi is positive. As that means what? Xi is positive, that means yi should be 1. Okay. Now the if x2 is negative, or because 2 plus c2, then what we can say, w2x2 plus b less than 0. And that is say that because of this, so yi is minus 1. Okay, so exactly this is, it is being given here, because this yi, this is the your output. Now given xi and yi in this particular setting, whatever we have discussed, given xy yi, we can say yi, that is yi, into, if we say w transpose x plus b, this is always greater than 0. You see that it is, both are 1, so both are positive, and if both are negative, that is also greater than 0. So always this equation holds. Okay. Now this is the case, and for unknown, so that is the query point, unknown feature vector, let's say p, this w transpose p plus b greater than 0, then p will be, p belongs to c1, or you can say p will be in c1, and if it is less than 0, p belongs to c2. So that is the type setup. Now the question is that if something equal to 0, just for example, now if we say that this wtx plus b is equal to 0, so this xi, let's say if you say x, xt, now this xt is on Hessian boundary. But now what we need, we need to maximize it, this decision boundary. So we have to change it, these equations of line that we said wtx I plus b, initially it is greater than 0. Now we can say there is a margin gamma. Okay, and what is the gamma? Gamma is the length of margin. Okay, now the question is that if we can see that that is the, this margin is gamma. Now find that the idea basically is that, now another thing that we are trying to find out. Now if this is the, this plus b is equal to 0, that was the, this line, this particular line. Now the distance of a point, from this line, from this particular line, is what? It is basically given WTX plus B by. So this is the that we'll see later also. So this is the basically distance between these 2 points. Okay. Okay. So here, I think please copy it down. Now, this is the idea. So now I just erase these things. Now you can see, this is the M is the margin, and you can say the distance between these 2 points. What we actually say is this into W. That actually we have said this is what, this minus this into W. This particular, this minus this by W. This is unit vector to W. So this is a very easy, simplistic way to that will do a mathematical, more you can say elaborate the next example. Now see that particular thing. There is a 2 data points. These are the you can say support vectors. So we put these two kind of guidelines, and this is the optimal hyperplane that basically are the main decision boundary, and this is the maximum merging concept. Now let there is a point U. So unknown U, the left side of the right side of the D. We don't know that. What is any point? Now what we're trying to say, we try to now how we can know that this particular U is which side of the decision boundary. So in vector representation, what we have to go, we have to project this vector U on the perpendicular to the decision boundary. So what is the perpendicular? You can say that this is the idea actually. Yes. Okay. So this is U. Let this is the point. Now the idea is this: there is a perpendicular with this decision boundary, and this is the perpendicular of this. This is the 90 degree. The 90 degree. So it's a perpendicular of this bisector. So it is a decision boundary, and this is a perpendicular. Now, if you project this U to this perpendicular to this point, now it is the left hand side of this. So if it is, you can say this is a positive, this is a negative. So U is basically this particular U is belong to a positive class. So you put the what, project this U on the perpendicular of the decision boundary. So that is the way. And if this may be U is maybe here, so then you can, if you the projection, then U is basically the negative side. So it depends on all this U, that how actually U is being defined. So actually, so if this is the, how you know this projection, how can you do this projection? This projection is this. Okay, so this U and this W. W is this particular perpendicular unit vector, the orientation of the unit vector of this. If it is greater, then is equal to C. So this is actually C. So C is basically this to this. If it is greater than is equal to dot product is taking a projection of u on w. This w is this perpendicular and dot product 2. And if it is greater than c, that we can loss of generality if we can say that this c, so we can say if this u minus c greater than is equal to b, and if you say let b is equal to minus c, so w transpose plus b greater than is equal to 0, then you can say this is the idea. Then if it is so, it's equal to greater than is equal to c, to greater than is equal to c means it is a, if it is a you can say, so we put a negative, so okay, so if this is the, if they actually ask this is a, so sorry, so this is equal to negative, this is positive, it's greater than is equal to c, so it is a positive example. You can write this is the decision. So this is the o means this, whatever, positive, negative, whatever. So then it is in positive. Positive means O. We say negative, so we make it positive. So any confusion? Or should I write? I can say again. Okay. So if anybody have any confusion, please ask, please repeat. Okay, no confusion. So it is very easy. So is greater than is equal to 0, then it is a positive example. And if it is less than is equal to 0, say this side is a negative example. Okay. But the problem is that we don't know the B and W. That is the thing. That this W we don't know. And this B, this C and B we don't know. And that is the problem. Sorry, not C and B is same thing. Basically same thing. C and B is equal to same thing, and C and W we don't know. W is the slope. Definitely this is the slope from that. This, what is this? Because this decision boundary we don't know. W and W bar is all know. As we know, we don't know. Only we know that W bar is a perpendicular to the decision boundary, but there may be many such W bar in different lengths. Definitely. Okay, so you understand that this is the way. Now, how to do that? So you see here in this, the same thing we're going to do. What I said. Now, this is the thing. This W vector, if dot product, this x plus means is a positive example. This is the data. This if it is a vector because it's a multidimensional data plus b greater than is equal to 0 because it's a positive example, and this w dot, this is negative plus b less than is equal to, is basically is greater than is equal to 1. So and it's greater than is equal to, there is a mistake here, less than is equal to minus 1. Okay, so this one, this minus 1 is basically a kind of the margin, plus 1 and minus 1. Okay. Now why I such that, why I said that if yi is equal to 1, if yi is equal to minus 1. Okay, so this is the thing. For in case of yi, this is greater than 1 because this is for the positive sample minus negative sample. So I can say this exactly, this into yi greater than equal to 0. What exactly we have done before? And yi into wx by minus 1 greater than equal to. So now the case is that if yi this be minus 1 equal to 0, then this data xi is on the decision boundary. Okay. That is that thing we see is the same thing. Now you see Now here, this is W. W is orthogonal to the decision boundary because this is 90 degree. This is 90 degree. So this is also 90 degree. What you can say, it's the same thing. So now the question is that, and what is this? The distance between, actually we're trying to find out this distance. So what we're trying to say, the width of the boundary. So this is this particular thing is what? This is actually this minus this. So this is x plus, this is x minus. So this is the thing. Width of this thing into x plus minus x minus into what? Into is w bar by this is unit vector. Actually, this is unit vector. Now, if we just add it, then it is wx plus minus wx minus by unit vector. Okay. Now, what is wx bar plus? We have formulated wx bar before. Is wx bar. This is wx. If you put wx, it is 1 minus b minus 1 minus b. Okay, by w. So 1 minus b plus 1. So it is 2 minus, so plus minus b plus b. So it is basically cancel it out, 2 by. That we have seen here. Here exactly this same thing. Now you understand from where it is coming. So this is the mathematical formulation of this. That this distance x minus x bar is basically 2 by w. So this is since this. Okay. So what we are trying to find out now, this we understand that 2 by 2 is basically. So now we formulate our problem of linear SVM that correct classify all the training data. So W, so for that the WXI plus B greater than is equal to 1 for if YI is equal to plus 1. WXI plus B less than is equal to minus 1. And this is if YI is equal to minus 1. And that means YI WXI plus B greater than is equal to 1 for all I. Okay. So this is, that is, so this particular thing is our function. And given this, we try to maximize m is equal to m, where the m is 2 by w. And so if this, the same thing is basically, this is the basically a norm. So if you say the 1 by, so minimize, it's maximize, so minimize 1 by m. So what is 1 by m? Half. This become half. And w norm is basically 1 by m, w transpose w. This is exactly this thing. Okay. So this is actually the constant satisfaction problem, constant objective optimization problem. So we can formulate a quadratic optimization problem and solve for W and B, and where this objective function is that psi of W is half of W transpose W, subject to constraint that yi W of xi plus b is equal to 1 for all I. Okay. Now you can understand that this linear SVM problem can be formulated. That how actually we are trying to find out this W and B, this problem given the data samples, we can formulate this particular problem as a constant satisfaction problem or constant optimization problem, the quadratic optimization problem with this constraint. So if you have any question, you can ask. That is the mathematical basis of linear SVM. Okay. So now it is already in a kind of very easy kind of thing. Now find W and B. Now it is becoming the problem inside. Now find W and B, because ultimate end of the day we have to know the training means training of SVM or LSVM, you can say linear SVM, to know is to know W and B. W and B. So W and B says that this particular thing, half of this W transpose W is minimized, and with constraint it for all Wi x yi, y into W transpose xi plus B square transpose. So this optimization problem for a convex quadratic objective subject to the linear constant. So it is a convex quadratic optimization problem that we are not going to prove here, because it is the out of scope of our discussion. But it can be proved that since the constant is linear, so this is become a convex optimization problem. Okay? So the convexity proof is out of scope of our discussion. The quadratic optimization problem are well-known class of mathematical problems and be solved using a quadratic problem. So QP we can use. The solution involves constructing a dual problem, because this is a constant optimization problem, and then any constant optimization problem can be make a unconstant problem by making a dual formation using a Lagrange multiplier. Okay, so we have to, the solution involves a constructing a dual problem where a Lagrange multiplier alpha is associated with every constraint in the primary problem. Okay, so we'll see this, how this we can make this particular problem, that is a constant optimization problem, that will make this particular problem the unconstant problem using Lagrange multiplier. That we'll see in the next class, because it will take another half an hour, and it will be confusing to you if I make it half done. So we'll do this in the next class. But in summary, whatever we have done so far, that if you see that the summary of this this linear SVM problem, that we try to maximize the margin with the help of these support vectors. And these support vectors, when we are trying to find out that how, given the support vectors, how we can make this particular problem as a constant optimization problem. So what is our objective? We find this margin in terms of W, where W is a unit vector, or the orientation of the vector is perpendicular to the decision boundary, this basically. And we can find that given this xi, so given means xi are basically, you can see these are the basically the support vectors, because support vectors is at the end of the day useful. Other data points is not much useful. So why for all y is because for support vector, if it is done, every other data points it can be done. So this yi xi yi, if we can find this particular thing, that this will actually, what is this you can have to understand, this is what, this is your decision rule, because This is going to, if it is a positive, then it will be greater than 1. If it is a negative, this will be less than 1 kind of thing. So this is our actually decision rule given these data samples. And these data samples, where is the important is that why support these are basically the for support vectors, it is very most important. Other data points, if support vectors is definitely other data points is left hand side of the support vector of the negative, right hand side of the positive. So that definitely there is no problem. And this is your maximum margin constant, or is that so? This is the objective function and the constant of this function. So this is solving the optimization problem. If you have any question, you can ask.
Excuse me, sir.
Yes, yes.
Sir, why is wx plus b greater than or equal to 1, meaning that it is in the positive class? Shouldn't it be greater than or equal to 0 because of that line?
Oh, that's basically what we are saying. This is basically what we have shown that we put here. Here you can see that we are trying to find out this particular, if it is a greater than this wx w dot x plus this plus b greater than is equal to 0, then only we can support this particular thing. Okay, but what we are want to do, we can take this. So these support vectors will be that. So w this, there is some sort of boundary this. Okay. And this wx dot x minus plus b, it is basically less than is equal to minus 1. So minus 1 is this. So our this in this case this is into 1. Okay, because that we have to say in between that, where we have said much. Why I actually out strike out this, rub out this thing. So this what we have seen now, this is equal to, so that particular thing we get a then equal to less than zero. So we considering this. So that's why this says that y is says that y is equal to plus 1 for positive sample, and so that is okay. So that is greater than is equal to less than is equal to 1. So if it is 1, that is okay, but this is due to this.
So we are just making it so that we can create that band. So can it be 2, 3 or
Yeah,
some other number also, or should it be only 1?
yeah, you can do that, but you can that you can do.
Okay, okay. Thank you, sir.
Okay, okay then. Thank you.